Okay, I think we'll get started. So today we're talking about generalized forces and generalized displacements, which will allow us to generalize our notion of work. And the reason for this is twofold. One is fundamental, and the other is convenience. Well, let's just remind ourselves of work, and we have this tricky issue of convention, sign convention as well. So in the physics books, work is defined this way, and so let's look at an example here with a spring. In our conventional way of defining this in the positive direction, this is the negative direction, x. If I pull on this, I'm doing work on the system. My dx, if I make a small change this way, my dx is positive. And my force is in this direction, so my force is negative. So that would give us an overall negative work. And that's the convention where we do work on the system and it's negative. Likewise, if the spring pulls me back like this, then the force is negative, dx is negative, and the overall is positive. So the system is doing work that's positive. So that's what we call the physics convention, and that's what your physics book, whatever one you have, will be using. Now, when we get into your chemistry book, probably won't do too much with work, but if it does, it might have the opposite convention where this is negative. And certainly when we get up higher and start looking at some real physical chemistry books, then the convention will be flipped. So we could have a negative here, and now that just flips the sign. So if we do work on the system, that's positive, and if the system does work on us, that's negative. So that's that sign convention. Now this is still the normal definition of work, which is force through a displacement. But we have all sorts of different contraptions that do work for us, and it's extraordinarily inconvenient to always have to trace back to a force and a displacement. And so that brings up this idea of a generalized force, something that's acting as a force and something that's acting as a displacement. And so we could see an example of that with, say, a piston device, and pistons play a huge role in understanding thermodynamics. We'll talk a little bit about pistons, but in this course, but later in the curriculum, after these introductory courses, pistons will be used a lot. And so if we think about what a piston can do, that's this container with one single arm that can slide up and down. And you can trace this back then by, say, you put a mass on here and that'll apply a force and a force. But what's really happening is you're changing the volume against a external pressure. So this is a pressure volume system rather than a force displacement system. So it would be convenient if we can work in the natural variables of whatever device we're talking about. If we have a battery, for example, that will push charge, and so the work that's being done there is an electrical work. And yes, we could go to Coulomb's forces and move those electrons, but it's more convenient to just work in the natural units of the charge and the voltage. So what is done is we define a generalized force and a generalized displacement. And I'm going to call this really fancy A. We're going to run into a fancy A down here, and then a regular A later on, not in this lecture. But and so this is the generalized force. This is the generalized displacement. So this could be F, and this could be X. Then that would be the real force and the real displacement. But any combination of these, and I shouldn't maybe say any, but a whole host of combinations of these, such that when multiplied together, they give us units of energy, will represent work. Now, if we have a whole bunch of different sources, so in a more complicated device, you might have electrical work and some mechanical work or or pressure volume work, then the work is just the sum of all the different components. So we might have a pressure volume work, we might have a electrical work, and so on. We just add up those components. Now, I mentioned earlier that in addition to this use by convenience or for convenience, there's a more fundamental reason, and we won't go into this too much, but it'll be a foundation of thermodynamics. So we will talk a bit about thermodynamics, but we won't have a full high-level course on thermodynamics till after these introductory courses. But we'll lay the groundwork here, and the key idea here is that all work, at least on paper, certainly not in real life, but all work is interconvertible. Maybe that's double. Interconvertible. And so what that means is we could have some electrical work turning into some mechanical work that pushes a piston, that changes into pressure volume work. And so we can go from one type of work to another type of work to another type of work. And at least on paper, that is 100% efficient. So 5 joules of pressure volume work, we could convert that to 5 joules of electrical work. And of course, in real life, there's going to be some inefficiencies every time you convert from one type of work to another. But that's just sort of a consequence of reality and the interactions with the environment and just imperfections in the machines. When it comes to theoretically developing these ideas, this is really important because what it allows us to do is to think about all work uniformly. So if we can do an analysis of, say, some very simple system like the piston system, which is typically done, then if we can do the thermodynamics for that, then we've done the thermodynamics for all work, at least in theory. Now, when you get to practical equations, then you have to go back to whatever type of work you were interested in. So there are these two reasons for this generalized force, generalized displacement. The notes have a little bit bigger table here. I've got just took some representative examples. Pressure volume work. That is of fundamental importance. Any book that does thermodynamics is going to be working in pressure volume work, at least initially, to develop the ideas. Voltage and charge. So we've already seen in Introduction to Physical Chemistry 1, we've started talking about charges. Introduction to Physical Chemistry 3 will have a lot more to do with charges and voltage. So very important systems. And we can see here the work expression for that. Notice the sign here. This is following the convention that if the system does work, that's negative. And then the same goes for these. Surface tension, we'll talk a little bit about that today, although we won't get into the details of why surface tension is what it is. And then chemical potential, this is something that's going to come up for us later on in this course, Introduction to Physical Chemistry 2. That's really important. And this is when we have changing the amount of material. And this can generalize then to multiple species, and that's how we're going to handle chemical reactions coming up. We talk about the work done in a chemical reaction. All right, well, let's just go through a few examples. 2 of these will be electrical based, but in different forms. And then 1 will be a little bit different take on things. All right, so there's going to be something new here, and I'll just tell you the formulas. We'll be getting to these in Introduction to Physical Chemistry 3. I think we did talk a little bit about two charged plates in Introduction to Physical Chemistry 1. But when we have these 2 charged plates that are parallel to one another, we have something called a capacitor. And there's a property associated with that capacitor called capacitance. And that's really the capacity to hold this charge difference. And we'll talk a lot more about that in Physical Chemistry 3, Introduction to Physical Chemistry 3. But when we have a charge difference here, we have a voltage difference. So these plates can be charged up by just hooking up a battery. And you're certainly familiar with a battery. If we hook up a 9-volt battery to this, then there'll be a 9-volt difference across those plates ultimately. The amount of charge that sits on these, so there'd be a Q, it's actually like this, Q and a minus Q, is going to be the capacitance, the size of that capacitor, times the voltage across that capacitor. And then we'll go to our chart here. What's our generalized force, generalized displacement? Work is voltage times dq. Now, we'll do just a little bit of calculus here. So you can follow that if you've had some calculus. Otherwise, just pop out the other side with us when we're through with that. So we have to build up this really small change with a small change in charge up to this full charge. And so let's actually instead here, let's get our Q's separated. So we'll say we're going to charge up to a value of big Q. So we're going to integrate up from 0 to big Q of this generalized force, generalized displacement to give us our total work. And there's the work there. And now we're dq and a dv, but through the capacitor, v is related to q, and so we could substitute this v here, do some algebra, get q over c, and then we have everything in terms of q and a constant. The capacitor, that's a constant property of the device. And so we're just integrating from 0 to big Q, Q. So that's like the integral of x. So we get x squared or q squared. Plug in the endpoints and we'll get this. So if you haven't had calculus, this is the result of the work to charge up that capacitor. Now, we can leave it like this, or because of this relationship between Q is just charge times the, capacitance times the voltage, and so we get, let's see. Oh yeah, that's right. And so we have these two different formulas for the work on a capacitor. All right, let's look at another example. This is still electrical, but instead of charging up two plates, we're gonna do what you probably do with a battery, put it into some device and run current through a load. And again, we haven't talked about the details of this, but just your own life's experience will be sufficient here. So we have a battery of a certain voltage. Let's call that VBAT. Notice I'm in both, I guess I should have mentioned this. We got a couple of V's running around. We got the V for pressure and we got the V for voltage. Try to make this fancy V for the voltage and regular V for the volume. Okay, so now we have the same work formula and we're going to integrate again. But now the voltage is constant because that's just the battery that you put in there. If it's 9 volts, it's 9 volts. And then we can integrate this up very easily. This is just the integral of a constant, which is just going to be final minus initial. And so that's going to be big Q. So big Q will be the amount of charge that is going through this load. Okay. Now, let's think about what are the charge carriers here. So this is the current, but we haven't worried too much about that. So out of here will come electrons, and they will go through the load like that. Each electron carries its charge, and so we learned about the charge of an electron in Introduction to Physical Chemistry 1. We've learned about moles, so let's let n be the number of moles of electrons. going through the load, and then 1 mole of electrons. This is called Faraday's constant, and this is just the charge of an electron times Avogadro's number. And so this is 96,485 coulombs per mole. So if we've got, say, 1 mole, then we bring this many coulombs. If we've got half a mole, then be half of that. So we have N times this fancy F, or cursive F, and that's going to be our charge. And then because the electrons are negative charge carriers, we have a minus sign out there. And so here's our work. And this is work done for a battery. Now we will come back to this in this course when we talk about the reactions that actually go on inside of a battery, so-called redox reactions, to generate voltaic cells. All right, our last example here, we'll look at this a little bit differently. Let's look at an example of a bubble in equilibrium. So if we think about what are going to be the components here of a bubble, well, it's got some volume, right? And then the bubble has some surface tension to keep the bubble together. So we're going to need a pressure volume, and we're going to need a surface tension word. So if we think about taking the volume from a radius of 0 out to some non-zero radius, then the components of work we can just write out as a sum. And so that's what this condensed notation is meaning here. Those are the contributions to the work. All right, well now, if we think about this bubble, so that's pretty straightforward, but it's a little more complex here now, more subtle, when we think about what does it mean for the pressure inside and the pressure outside the bubble at equilibrium. So let's just think intuitively about that. If there was no surface tension on the bubble, then, so if we imagine this sort of artificial case where there's no surface tension, if our bubble is not growing or shrinking, then the pressure inside is equal to the pressure outside. Because if the pressure was inside, our bubble would be growing. If pressure inside was greater than outside, the bubble would be growing, and vice versa. So we would have equal pressures. But the surface tension is a restorative force. It's kind of like a rubber band, and that's going to want to squeeze the bubble. So when we have a non-zero surface tension, which any bubble would have, that's going to squeeze in the pressure, or squeeze in the bubble, and that will increase the pressure inside versus outside. So the equilibrium bubble, where it's not expanding or contracting, will have a pressure that's greater inside than outside because of that surface tension. And so that's what I've got here. If we take this, pretend that we had 0 surface tension, then our pressures would be the same, but non-zero pressures would be different. So let's think about a infinitesimal amount of work here under these equilibrium conditions, and we'll call that, this is not dW, we'll call this dWA. And so we're going to now try to change the area, and what's that going to do? Well, that's going to be fighting against the pressure difference between in and out, not the pressure external. So again, kind of difficult here. If we're building up from 0, then we're pressing against that. We have a press against the external environment. We also have we're pulling against that surface tension. But now we've got an equal or near equal pressure inside outside. So if the bubble were to move, right, we have the internal pressure that is, in a sense, helping that bubble stay intact in addition to the surface tension. And so what matters here is the pressure difference. Now, the change in area and the change in volume are related, because if the area changes, the volume changes, and there's no way to uncouple these. So these are coupled together, and we know the formula for the volume of the sphere and the surface area of a sphere. If you've had some calculus, you can probably really easily see that a small change in volume and a small change in area are of these formulas in terms of dr. So if you've had some calculus, you would just take dv dr and then bring the dr over to the other side. And so now we've expressed both of these in a single variable, r. It's the radius that will determine both the volume and the area. So we can set these equal to each other. So we have gamma dA. So here's our dA, and then we have P, the difference in pressure inside versus outside, and then here's our dV. Well, a lot of things can cancel here. The pi's, one of the r's, the 8 becomes a 2, and that cancels. And then we can solve for the pressure difference inside versus outside. And so we get a formula associated with bubbles that the internal pressure versus the external pressure then is 2 times the surface tension, and divided by r. So let's think about this a little bit and gain some intuition. Let's recover this case. If gamma is 0, then the difference in pressure is 0, so that certainly makes some sense. If gamma is really big, then that's going to squeeze that bubble, and the pressure inside will be much bigger, or significantly bigger than the pressure outside. Let's look at the effect of r, though. That's interesting too. So if we have a bubble of radius r1 and then a bigger bubble of r2, and everything else the same. So the same molecules that make up the surface of the bubble here. So gamma is the same. But notice the internal pressure is much big. The difference in pressure, so P in minus P out 1 is greater than P in minus P out 2. So the smaller the radius, the more effect that fact that we have surface tension gives. And as the radius goes out to infinity, then basically we have a infinite sheet, and the pressure difference on one side of the sheet and the other side of the sheet goes to 0. So if r goes to infinity, the pressure difference goes to 0. All right, so this is the idea of generalized force, generalized displacement. And again, then to summarize the big picture, this is done for 2 reasons. One, for convenience. So when we talk about real systems that we're interested in what they're doing, it's nice to have the work expressed in things that are actually related to the system, instead of always having to track your way back to force and distance. And then secondly, more fundamentally, that all work is interconvertible, and thus as we want to think about one or another individual types of work, when we're thinking about this in a general framework, we can think about all work as being one single thing, and we can use whatever convenient form we would like. Typically, that's going to be pressure volume work when we talk about more advanced thermodynamics.